Welcome to section 15.8. Okay, gentle people, what I would like to talk about now is collision theory. So again, remember, a theory is something that gives us underlying ideas, and now we want to talk about the underlying ideas behind kinetics and what affects rate. And so, as chemists, we like to think about bond breaking and bond formation. Now, for bonds to break and bonds to form, one of the things that can happen are molecules can come together, they can impact each other or run into each other, and this collision leads to bond breaking and bond forming. And so the idea behind collision theories is that when we talk about the rates of reaction, if we're talking about a reaction proceeding forward, we need molecules and atoms to actually collide, impact each other, and then this results in a reaction. And it is only when I have this collision do I have bond formation or bond breaking. Now, if we go ahead and think about collisions, we just don't say it's any old collisions. We have to have effective collisions. Now, there are two main things to consider when we want to have an effective collision. And those two things are orientation and the energy of that collision. Now, I'm going to talk about these two things in the upcoming slides, but I want you guys to remember Chem 1A, back in chapter 5, we talked about temperature. Now, remember that temperature is the measure of kinetic energy. And so temperature has a big effect in collision theory, because not only is it kinetic energy, so that is the energy component of the collisions, but remember that kinetic energy is actually measuring the velocity of my particles, my molecules, and atoms. And the faster my molecules are, well, that means the more collisions I'm gonna have. And so you guys can go back to chapter 5, and you guys can go ahead and look at the equation for frequency of collisions, and you can see how that is affected by temperature, and it's going to come into play when we talk about kinetics. So in the previous slide, I said that collision theory is all about effective collisions. And so there are two factors that come into effective collisions. One of them is orientation. Now, before I get into the slide, let's go ahead and think about a small little analogy before we hit the slide. So the analogy that I want to use is a real simple one. I want to go hammer a nail into a plank of wood. I'm going to use a hammer. Now, one thing that I'm going to do when I use this hammer is I'm going to use the correct end of the hammer. And so I'm going to use the hammer head because I know that this is way effective when trying to hammer this nail into this thing. And so if I orientate my hammer the proper way, I should be able to drive that nail in right quick. However, what would happen if I go ahead and use the wrong end to the hammer? So I take this hammer and I turn it around and I try to hammer that nail in. Now, I'll still be able to drive that nail in, but I'll do it at a much slower pace. And so this idea here is that if I have the correct orientation of things, things will proceed faster. So let's bring this to molecules. And so here's the reaction that I want to have occur. I'm going to have this molecule right here. And in this molecule right here, what you guys will see, it's made out of a green sphere, a blue sphere, and a red sphere. Now, what I want to have happen is I want this green sphere to come in and I want it to form a bond. And what it's going to do is I'm going to extract two green spheres attached to each other. So this is my new chemical bond. And then I want to go ahead and split apart this green and blue sphere. So that's my bond breaking. Now, if I want this reaction to proceed, well, I need the green sphere to come in and I need to hit it at the right space. And so in this case, the correct orientation is if the incoming green sphere actually hits the green part to the molecule, and then I will have an effective collision. Now, an ineffective collision is if this green sphere comes in, but then it collides with the red part of the molecule. I'm not forming a red-green bond. I want to form a green-green bond. And so what happens here is as soon as it hits the red part of the molecule, it's just going to bounce off. So even though I had the collision part to here, I didn't hit the molecule in the right way, and so I won't proceed forward in my reaction. So this leads to the reaction going forward. This does not. This is going to make my reaction proceed faster. These type of collisions are going to slow down my reaction, or in other words, I'm not going to go forward in that reaction. All right, so let's go ahead and think about some of the stuff we learned in chapter 5. So this graph might look familiar to you guys. This is the Boltzmann distribution at 2 different temperatures. Now we have temperature 1, which is in blue. It is our cooler temperature. And we have temperature 2, which is in red, and this is a hotter temperature. So remember what happens when I heat a distribution up. So if I heat temperature 1, what happens, or what doesn't happen, is I don't translate the graph. Even though I'm at a hotter temperature, I still have a certain amount of molecules that are slower moving. It's just that I have less number of those slower moving particles. What matters is if I start looking at higher energy or higher velocities. What you guys will see is that I will have more high velocity particles or more high energy particles. Now, with this idea, we can talk about a concept that we kind of skimmed over previously, and that was the activation energy. So let's go ahead and talk about a reaction coordinate diagram. So this is the reaction progress. On this side, I have reactants. On this side, I have products. Now remember, in kinetics, we care about the path. So I want to go and take my reactants to products. Now, to get from reactants to products, I have to break bonds, I have to form bonds, and that takes energy, and that's going to be called our activation energy. And so this is the threshold energy that I have to overcome for reactants to become products. Now, the bigger this activation energy, the harder it is going to be for reactants to go to products, and the slower my reaction is going to be. And so the analogy that I gave you guys before is, think of cars going from place A to place B, and then there is a mountain in between them, and depending on how high that mountain is, that will tell me how fast the cars get from point A to point B. So now that we have set up our activation energy, let's go ahead and bring in that last graph that we talked about, but this time I'm going to go ahead and turn that graph on its side. So what you guys will remember is this is the Boltzmann distribution. So here are my number of particles up on top. And what you guys will see right here is the cooler temperature and the number of particles that have enough energy to overcome this threshold energy. These are the particles that are going to make it over the hill and actually go to products. But now, if I go ahead and increase the temperature, what you guys will see is a larger percentage of my reactants have enough energy to overcome this threshold. And so what this means is that the higher my temperature is, the faster my reaction is going to be. And the reason it's faster is because more particles have enough energy to overcome this activation energy. So why don't we take a brief interlude and tackle this quiz question. So what I want you guys to do is tell me, how can I express the activation energy going in the reverse way in terms of delta H and the activation energy, and use this graph to help you guys out. All right, let's go ahead and take a look at this reaction coordinate diagram and try to explain the parts to it. So we have our reactants and our products. So remember our thermodynamic value, if we want to go from our initial state to our final state, we don't care about the path, And then thermodynamics, if we're path independent or a state function, we can describe one function, delta H. That is the enthalpy of that reaction. So that's just the difference in potential energy from reactants to products. Now, kinetics cares about the path. And so what I can say is going above this activation energy and down right there, this amount of energy is the activation energy for the forward reaction. So I'm going to go ahead and call that forward EA. Now, what I'm after is I'm after the process going backwards. And so the reverse process means I'm starting on the products and I have to overcome the mountain. And to overcome the mountain, I have to go all the way up here. And this is the threshold energy that I'm going to talk about. So if I go ahead and look at this threshold energy or the activation energy for the reverse reaction, so let's go ahead and write that. So that's reverse activation energy. The first little leg of my journey is I have to overcome delta H. And the next part of my journey is I have to overcome this EA, which I previously described as the forward activation energy. And so if that's the case, then I know that the correct answer is this one, choice B. So now that we've talked about these two ideas of orientation and activation energy, let's go ahead and put it into a grand equation. And that equation was described by Arrhenius. Now, kind of an interesting little side note is Arrhenius did his work right around the 1890s. And around that time, he actually predicted the greenhouse effect and the problem with producing too much CO2. So this idea of climate change is more than 100 years old, and you can kind of say that he was one of the first people to actually convey his concern about the production of CO2. But let's go ahead and talk about his equation and how it pertains to chemical kinetics. So what we're going to do is we're going to go ahead and look at rate constant. So that tells us how fast a reaction is going to occur. And what Arrhenius said is that our rate constant K is going to equal A, which is called our pre-exponential factor. And this is going to be times E to the minus EA. So here's our activation energy. R is our gas constant. And then T is going to be our temperature. Now, usually you're going to put temperature in Kelvin. R is going to be the 8.314, and that's because activation energy is measured in joules. So you want to make sure you cancel that unit out. So let's talk about this one weird kind of variable in here. This is the pre-exponential factor, or sometimes called the frequency factor. And it is made out of two other terms. One you might have seen before, and that's the collision frequency Z. And so this is the number of times particles are going to collide. Now, it's not effective collisions, it's just the number of collisions. What I will say is that we are going to times this by P. And so what P is the number of collisions with the proper orientation. So what A is really measuring is A, the pre-exponential factor, is the number of effective collisions. So now what you guys can see is the Arrhenius equation brings all the ideas of collision theory together. It has effective collisions. It notes that there is an activation energy and that there is a temperature dependence. And the more hotter that I am, the higher K is going to be, or the faster my reaction is going to be. And it brings it into this one grand equation. Now, one thing we should note with the Arrhenius equation is this is E raised to some power. And so if we wanted to graph this, this becomes a curve. And what I've been telling you guys since Chem 1B is that we don't like curves too much. So what we can do is we can go ahead and rearrange the Arrhenius equation. And what you guys will note is we're going to go ahead and do what we always do and put this to an equation of a line. So y equals mx plus b. And so what we want to do is that on our y-axis, we are going to go ahead and plot the ln of k. And then on our x-axis, we are going to go ahead and plot 1 over temperature, and that can get us a straight line. Now you guys can look at what our slope is going to equal to. Our slope is going to equal the negative activation energy divided by R. And so what you guys will see in the next slide is what's called an Arrhenius plot. So figure 15.14 in your book is an Arrhenius plot. So again, to remind you guys, if I graph the ln of my rate constant over the reciprocal of temperature, what you guys will get is an Arrhenius plot. Now, we should get a straight line, and that straight line will help us calculate our activation energy. Now, this is one way to do chemical kinetics so that we can calculate activation energies, but we can actually do a little bit more manipulations on this, and we can do something that we did similar to the Van Hoff equation. So what I can do is I can take two of these Arrhenius equations and subtract one from the other. And in doing this, what I can do is I can eliminate this pre-exponential factor, and what I do is I get this new equation right here. Now, what's beautiful about this new equation right here is I have my rate constants and I have temperature right here. And so what I can do with this equation is I can tell you how fast a reaction is, or in a little bit more specific terms, I will tell you how much I can change the rate constant by changing temperature. And so while the Van Hoff equation tells you how much product you're going to make, this equation is going to tell you how fast you're going to make that product. So if you guys are working in a chemical plant and they say, I want to raise the temperature to produce more product faster, well, you can give them a breakdown as how much the temperature is going to affect K, our rate constant. So let's go ahead and practice with that new equation. I'm going to be working at this chemical plant, and let's say that we want to see if we can save money by not running our reaction so hot. So I know what my rate constant is at 370 Kelvin, and it's this. I want to talk to my foreman and say, well, let's go ahead and explore the idea of cooling the temperature by 60 degrees. How slow is our process going to actually be? And so here's our activation energy. So go ahead and crank this equation out with these numbers. All right, gentle people, just like the Van Hoff equation, we're going to write down our equation first, and we're going to go ahead and organize our data. So I've got my activation energy over R, and I'm going to put 1 over T1 minus 1 over T2. And so let's go ahead and organize our data right here. So we're going to say that K2 is going to be my new rate constant that I'm looking after, and this new rate constant is going to be at 310 Kelvin. Now I have a rate constant of 7, and I know that this occurs at a temperature of 370 Kelvin. And just to remind you guys, I don't have to make this T1 and K1. I could have made that K2 and T2. The importance here, just like the Van Hoff equation, is you be consistent and you always put the K that is associated with that temperature. Now, one thing to note is that we've got to put our R, and our R is going to be 8.314 joules per Kelvin per mole. Now, the next thing we note is the reason I use that joules is that because I want to cancel out units, and EA is usually measured in some form of joules. Now, I'm going to give you guys a little bit of a warning. Activation energy is not usually measured in joules, but kilojoules. And so to cancel out units, I'm going to go ahead and change that into that 900 kilojoules into 900,000 joules. So now that I've got all my stuff, let's go ahead and plug it into the equation. So that's going to be the ln of K2 over 7 equals 900,000 over 8.314, and this is 1 over 370 minus 1 over 310. And in this case, K2 equals 1.79 times 10 to the negative 24th. And just to be consistent, the units on this will always be the same units that you had before. So in this case, we were given our K1 and it had units of per molar per second. And so we just want to keep those units. But what I wanted to show you guys here is kind of the dramatic effect of changing temperature. And here what we went to is we went from 7 to something that is 10 to the negative 24th. So if my foreman was interested in dropping the temperature at his industrial plant by 60 degrees, well, he's going to expect things to go times 10 to the negative 24th slower. So this might not be the best option to do in this particular case. I hope everything made sense. And again, Chem 1C, stay safe.